All right, everybody. So, welcome back to Desmos, where we were graphing the rise in cases in the US of the coronavirus. And you can see as we went through, I think, the 59th day, we got a pretty nice fit for an exponential function, which made a lot of sense to us. Now, in my last video, I showed you that when we graph the days after that, it really appeared to have a logarithmic feel to it. And so we shifted and modeled that with a logarithm, thinking that it was going to rise in this logarithmic way over to here. But you'll notice our prediction for the 67th day was right around here. It was about 85,000. But then what actually happened in the data from the World Health Organization is the next day there were 188,500 cases. So here is the official data that we were looking at, and you see this curve here that we were modeling that then had an enormous spike up to here. Now, I think that if you research some things and look into some things, you can brainstorm some reasons that this spike happened and why there's an apparent um, inflection value that we were getting pretty excited about in the math that we saw before, whereas now it's a return to really looking like an overall exponential growth situation. So again, if we go back here, notice that our original exponential graph comes very close. It is higher than this red dot, but not by as much as we thought. We thought we would be down here, and we're actually about double where we anticipated according to our modeling the day before. So that alone is very interesting. But it also highlights the idea that you can't just model these kind of things with exponential growth or with logarithmic growth because it's not really what's happening. So that's why we've introduced the SIR model, and we've started to look at that. So what I've done is I've built a numerical solver for you for the SIR model. Now this looks very, very complicated, but I'm going to walk you through this Google Sheets to show you how this is calculating what's going on. So first of all, this first column is the number of susceptible people. And then we have S prime, that is susceptible, the change in the number of susceptible people per day. Then we had the number of infected people. Then we have the change in infected people per day. And here we have the removed people, the people that have been removed from both the susceptible and infected populations. Here are our columns for alpha and beta. Here's the total number of cases. So this is usually what's reported in the media, sort of, is they report the total cases. They don't really report the number of currently infected. Very often they'll do the number of infected plus the number of people that have already been removed is the total cases that we have so far. And you'll notice over here, we have another column that says 20% of the total cases. So all this does is do 20% of the number next to it. And that's because I found through some research that it appears that only about 20% of people that are getting the coronavirus are actually being tested, are actually bad enough to go to the hospital, and then those are the people that get tested. So 4 out of 5 people that get this virus just have very mild sicknesses or no real symptoms at all. And so that means they don't end up getting tested. So the numbers that are reported would actually be in this column, whereas the total number of cases that are really happening would be modeled better by this total cases column. Now, if you go over a little further, in the one that I'm sharing with you, these are the only values that you can actually change in the entire sheet. So I've locked the rest of the sheet so that you can't change the equations and make things work in a different way there, but you can pick an alpha and pick a beta. So that's why those are highlighted yellow, so that you can change those numbers and see what happens. Now, here's the idea of what this does. We had to start with an initial amount of susceptible people. So I started with the population of the United States. We had to start with a number of infected people. So I started with 1. And we started with 0 people removed from the population. So what these other columns are going to do is they're going to do exactly what our SIR model said. So we're doing minus alpha times S times I. Here for the infected, we're doing the negative of what S prime was minus what R prime is. And if you look back at the equations, that's really how I prime is calculated. Then for R prime, we're just doing beta times I, the beta value times the I column. Okay. So these initial alpha and beta are just, alpha is calculated by taking the alpha that you pick from over here and dividing it by the population. Beta is just taken directly from what you have picked over here for your beta. So here's the idea. If we look at putting in our alpha and beta, we can go through and look at the number of infected people per day, and we can see as this column here is the number of infected people how it rises. We're getting up into the thousands, hundreds of thousands, millions, and then it actually at some point starts to decrease. That's very interesting. So see how now it's much lower, right? It's no longer in the millions. It's hit a peak over here. So where does it actually hit the peak? Well, we have to look at I prime to see that. So right here, you see how we did have a positive I prime, and then it shifted to a negative I prime. Well, at that moment, that's where we hit the top of the curve in our infections. So it's very interesting. So you can go through and change the alpha and the beta, and you can look at what's happening on this and look at the numbers, see how they go up and down, and really see how everything is calculated. So every column is calculated just using those SIR model equations that we developed in the previous video. Okay, so that's really nice. As you change these, it will change the numbers here, and you can look through what's happening. But probably a better way to go about this is to use this other website that I've put in, made by Warren Weckesser. And this was made back in 2005, so this is actually accurate for any spread of any disease using the SIR model. And you can put your values in. Now, alpha, they named R, and beta, they named gamma, but don't let that bother you. They're still the same situation that we have. For initial conditions, all you need to do is pick a percentage of people in the susceptible to start with, and a percentage of people written as a decimal, as you can see. And then you can make this the maximum duration. It shows you how many days this is going to run for. So if you set up this initial version and hit show solution, it'll show you the graphs like I showed you in the previous video. We have the susceptible people going from 100% of the population going downward. We have the recovered people going from 0% of the population upward, and then directly below this crossing point we have the apex of our infected curve, and this infected curve would imply that about 25% of the population would be infected right around day 60, all at the same time. 25% of the population would be infected, and that would be a lot. So we hope that this is really a very worst case scenario, and that really we have this curve flattened. And so what I'd like you to do is go into our model and try to change these numbers to see how you can flatten this curve in different ways, and describe that to me in the comments, or write something up for me to show me what you've determined. Now, beyond just changing these numbers, I mean, I recommend changing the numbers for a little while first, but once you've done that, really start to brainstorm the issues with this model, why we're calling this a simplified model. Because the more that you play around with this model, I think the more you're going to see the issues that this is not taking into account. And that's where the discussion can get very interesting. So let me know in the comments or let me know in an email if you have any issues or problems or questions. I would love to discuss anything that you find and anything that you're interested in through this project.